entitled Dinosaurs, A New Vision of the Future. So without further ado, assuming the IT is all now sorted, I'll hand over to Professor Benton.
Thank you very much. Just as a kind of introduction, I've got three themes that I want to talk about. Number one is, this is the 25th anniversary of the first discovery of dinosaurs in China, only 25 years. And yet, since that time, we've become used to fantastic new discoveries almost every week, including feathered dinosaurs and some other pretty amazing things. So I'll talk about that. Secondly, it's a little bit, as Malcolm indicated, about how do we know what we think we know. So if you think, how on earth can you know the color of dinosaurs? Well, I'm going to try to explain how we do. And this is about evidence. And the third thing is just the fact that putting together the new discoveries with the new methods, we can images of dinosaurs with skin, feathers, armor, colors and patterns, each of which features we can provide evidence for. So let me see if I can advance the slides. Yeah, am I getting there? I think we are. Here we go. So the story begins then 25 years ago, well, 26 years ago now. But the book came out at the end of last year, and it coincided more or less October 1996. This was a scientific meeting I attended as a younger person. It was the annual meeting of the Society of Vertebrate Paleontology, which is the international professional body representing my subject. It was held at the American Museum of Natural History that some of you may have visited on the edges of Central Park in New York. And something unusual was going on because during the meeting, this article appeared in a prominent place in the New York Times. And the writer Malcolm Brown is a well-known science journalist, and the New York Times prides itself in being reliable. And the text there, as you see, is describing something that's being shown at the meeting. It looks like a dinosaur, but it's got feathers, and that's in his heading. What does this mean? And at that time, that was a very radical proposal, because of course people know that only birds have got feathers. And the unusual thing about this article was it's not reporting a paper that was being presented at the conference or a poster or any other official presentation. It was reporting sort of rumors in the hallways. He's talking about crowded hallways and that sort of thing. And so what was going on was that a Chinese professor, young professor Peiji Chen, was at the meeting. He had photographs of this specimen that he was showing to people. And the whole thing is about 1 meter in length. So quite a small beast. And obviously a dinosaur. You can see its long tail and its long legs and the shape of the head. It's a small flesh-eating dinosaur. And it's got short arms. And yet he noted, of course, all the way along the back and in tufts down the tail were certain structures, which I'll show you in more detail in a minute. And he was asking people, could these be feathers? And people very rapidly fell into two camps. And this is what the journalist was reporting. Do we believe it? You know, could this be a dinosaur with feathers? Or more commonly, yeah, it's a dinosaur, we can see that. But clearly these are not feathers because only birds have got feathers. Unknown to almost everybody at the meeting, except for Phil Curry, who was mentioned in Malcolm Brown's news item, almost on the day that Malcolm Brown reported, this dinosaur, or should I say this specimen, was named as the world's first fossil bird from China. And it was called Cirencester prima, meaning Chinese reptile wing, the first. And it was described by two professors at the Geological Museum of China, both of whom had the surname G. So G and G, 1996, there's the full title of their paper. It was in its original form, it was in Chinese language. This is a later translation. And they are very definitely assigning this thing to birds. Aves Linnaeus, 1758. They are calling it, and the title of the paper, the first bird, because it's got feathers. Even though the front limbs are so short, it obviously is nothing like a wing. And this was their specimen located in the Geological Museum in Beijing. And 2 years later, Chen was able to publish his paper in English in Nature. This was the first of a big run of papers in Nature that drew the attention of the world to these amazing fossils from China. There's his specimen. I should have clarified he was at Nanjing. So this is the Nanjing specimen. He couldn't name it because he realized this is Sinosauropteryx. I can't give it another name. And so he brought the name Sinosauropteryx into the English language for the first time, because even by that point, very few people were really aware, outside China, were really aware of that first paper. But what was going on? A bit of skullduggery, it seems. Look at that Nanjing specimen on the left. Look at that Beijing specimen on the right. They are, in fact, one and the same. Because if you're looking for fossils in these rocks, they're in very flat, shaly sort of rocks, and you split them open with a hammer, boop, and some very smart dealer realized they could make a load of money if they went to the two leading museums in the two leading cities of China and made no mention to either side. Oh, by the way, there's the other half, but we're just going to sell you one half of the thing. And so it took a year or two before actually people finally realized. Phil Curry, the famous Canadian dinosaur researcher, knew because he'd been in Beijing just before the New York meeting, and he'd actually seen the Beijing specimen, and he told them, it's not a bird. You know, it may have feathers, but it's not a bird, it's a dinosaur, very clearly. Anyway, so that's how it all began. And that made a big impact on the world. And so this is one of my themes of how this new Chinese material has massively changed our views. But we need to go back to what was the state of knowledge at that time. And it's fairly commonly known information, actually. All we really knew was Archaeopteryx. If we wanted to know about the origin of birds, we have Archaeopteryx, famously from quarries in South Germany. Here's one of the specimens, and there are a number of them were found in Victorian times. And in fact, the timing couldn't have been better, because the first one was found in 1861. And that was 2 years after Darwin's On the Origin of Species. And in that book, which of course gained a huge amount of notoriety and fame in equal measure at the time, he talked a lot about fossils. And he said, we expect that fossils will show us intermediates between the great classes of life. And so he was making a very definite prediction, which has largely been borne out. And indeed, Archaeopteryx came along as the perfect missing link, a term that people commonly use. Because as Thomas Henry Huxley said, and that's his portrait, this is a dinosaur in bird's clothing. So Huxley was a comparative anatomist and a paleontologist, and he had studied many dinosaur skeletons. And so when he first got a sighting of these new Archaeopteryx fossils, he said, well, all the bones of the skeleton look like those of a small, lightweight dinosaur, just like Sinosauropteryx, as it happens, except that it has very obviously got feathers. And yet, not much was discovered between the 1860s and the 1990s. You might have thought we would have found a huge amount of additional knowledge, information, but we had not. And more or less what I had to teach my students in those days was, we know that birds originate from dinosaurs, but we only really have Archaeopteryx as the intermediate form. And whereas we have at the bottom of the tree loads of dinosaurs, and at the top of the tree loads of birds, the modern types of birds, and I put the range 75 million years because there's a reasonable fossil record of birds back to about 75 million years ago, but they're all the different modern types, you know, a penguin, a parrot, a perching bird, whatever, a chicken, whatever. And then there's a great gap, then there's Archaeopteryx, and then another great gap. So the Chinese fossils massively filled up our knowledge. And this is what the localities look like. The fossils come from the north of China, And on the map is Beijing. You can maybe just about make out as the little red spot. And Liaoning province, right up against North Korea, is the main source of these fossils. And the rocks in the field look like this. They're great thicknesses of limestones and mudstones, thinly bedded, and they are in fact ancient lake deposits. So if you've got a faint memory of geography lessons, they are showing varves. These are varves, or layers that represent seasonal conditions within the lake. And I can't recall whether these varves represent a year each or some longer span of time. But the rocks are absolutely full of fossils. And this one locality, Siheton, yielded thousands of specimens of fossil birds. So we get excited about Archaeopteryx. It was the $10 million fossil. There are about 12 or 15 of them ever found. Here's one quarry that's produced 1,000 fossil birds of similar quality. And so the resource is just amazing. You know, the addition to knowledge is fantastic. And these fossils, they're generally called the Jholebeds. These fossils cover all the different things that you would expect to find in a lake. In other words, fishes and various plants and other creatures that would be living in the lake, insects, birds, pterosaurs, the flying reptiles and so on that would be flying above the lake, as well as a few dinosaurs and mammals that might be in the trees and so on around the lake. It's kind of sampling everything. And it's not just one lake, there are multiple lakes, and these deposits go over hundreds, if not thousands of kilometers. So enormous area of the north of China in which these fossils are found. And the preservation is fantastic. There's a bird with stomach contents. We can see that it was eating a certain kind of seeds. The seeds can be identified. We know exactly what it was eating. Other examples would have fish bones or insect remains inside. And the exceptional preservation is because these lakes were relatively undisturbed. They were quite gentle deposition, no great storms, but mainly it seems they're close to a lot of volcanic eruptions. So that a lot of that gray color is from ash, volcanic ash that is being kind of washed in and kind of reworked in the lake. And that makes the sediment slightly acidic, and that tends to preserve some of the soft tissues, just like the bog bodies that you'll have heard about. So here is Sinosauropteryx. It was the first to be named, 1996. The fossil again, a reconstruction of a happy-looking Sinosauropteryx running along, liberally covered in whiskery little feathers. And here at last are close-ups of these so-called feathers. Chen, in his Nature paper, called them proto-feathers. He was sort of hedging his bets. Although I would say if it's a proto-feather, it's a feather. It's a feather pretty much. But people did debate, what are they? And you can see along the tail, the vertebrae of the tail run up the middle, and the feathers are in sort of regular bunches, tufts. The opposition view was these are shredded skin, and we had to hold to that for the moment. You couldn't really say for sure because they're so simple. However, in 1998, the second of these weird creatures was announced, a very strange looking thing in the reconstruction, but this clinched it for most people. It belongs to another dinosaur group altogether. It's got feathers, but it's also got complex feathers, contour feathers, or veined type feathers. So, you know, there are multiple kinds of feathers on birds, simple whiskery ones, fluffy down feathers on the breast where they branch from the bottom, and then the sort of contour and flight feathers, which are really complex. They have a rachis or quill, and they have the barbs and all the other structure that we're familiar with in a feather. And Caudipteryx already has those on its tail and on its wing. These cannot be interpreted as shredded skin because they have all the complexity of the structure of a flight feather. Microraptor, 2 years later, the four-winged flying animal. So whereas the other ones clearly could not fly, this one almost certainly could. And right from the start, people said, my goodness, look at the area of the wing in proportion to the body size. I bet this thing could take off and fly. And it's not only got 2 wings, it's got 4, which is completely crazy. This is another weird experiment in flight, maybe. And the fossils are just exquisite. The detail is there. Under the microscope, at any magnification, chemical analyses, these are feathers. They are not traces of some bit of chance mud or skin or something else. Loads of birds. I won't talk about them in any detail. There's a couple of specimens of Confucius Ornis. Already we're getting ideas that perhaps the males had long tails that they may have used in sexual display, just like so many birds do today, and the presumed female on the right. If somebody had found a double Archaeopteryx specimen, they would have gone completely mad, and yet this kind of thing is almost commonplace now. But just as a first step, what does all this mean? Well, the first key point is it's filling up that knowledge of the fossil record that we had. Remember the diagram where you've got Archaeopteryx and then a long gap below and a long gap above. These gaps are all filled up now. And not only are they being filled with fossils that show us all the stages right up to Archaeopteryx and then the stages from Archaeopteryx up to the modern types of birds, they also allow us to study the function and the evolution of function. Because when people found Archaeopteryx, they realized this thing could fly. It's a fully fledged flying bird. But that doesn't help you in understanding the detail of the origin of that massive and important innovation. These fossils do, because as shown in this Scientific American illustration, we've now got a whole sequence of forelimbs of dinosaurs and other creatures up to Archaeopteryx and beyond, some with feathers, some without feathers, and of course you can reconstruct and then somebody who's expert in aerodynamics can work out the quality of flight that might have been possible for these creatures. And the richness of data also allows us to explore evolution of body size, and we discover that whereas most dinosaurs specialize in getting bigger and bigger, and the yellow blobs are things like T-Rex and the other giant flesh-eating dinosaurs, along the line to birds shown by the silhouettes, there's a very definite trend of miniaturization. So the way that flight was achieved, it's a balance between wing area and body mass. And in order to be able to fly, your wing area has to be sufficient to lift and hold aloft the body mass. And you can achieve that by two means. You can either grow, if you're an animal, you can evolve to grow enormous wings, or you can get smaller, but keep your arms the same size. So if you start out with little wings, but your body gets smaller, it reaches a point at which you can fly. And that seems to have been actually counterintuitively how it happened. And indeed, picking that idea a couple of years ago, Pei and colleagues published this extraordinary paper where they showed that powered flight actually originated multiple times amongst these feathered dinosaurs. So we've got Archaeopteryx and its relatives here at the bottom, but there's a whole bunch of other things, including Microraptor, the four-winged thing. There's another mad-looking creature here that looks almost like a bat, but it's actually a dinosaur. And it was achieving that wing area by having membranes, just as bats do. So in fact, there were 4 or 5 experiments. The greens indicate different ones that aerodynamically could fly. This was based on those very calculations of estimated body mass versus measured wing area. And you can measure the wing area in the fossils. There's no question about that because they're preserved. You've got the feathers, the membranes, whatever else. The body mass has to be estimated. We can't weigh the fossil. That would be pointless. But nonetheless, you've got the whole skeleton of the body. So it's not unreasonable to take that skeleton and match it with living birds and so on. And we know the weight of a pigeon. And if you've got a skeleton, a fossil skeleton that's exactly the same size as a pigeon's, and the bones are hollow and there's other weight-saving features that they have, it's not unreasonable to say probably this fossil weighed the same as a pigeon. And then you can determine what the ratio is between body mass and wing area. Could it fly if it's just over the threshold or not, if it's below the threshold? So that's one thing. We can determine flight originating multiple times. That's new. That's crazy. And there are all sorts of things evolving to become flyers, presumably for adaptive reasons. They were specializing in eating insects, climbing in trees, things like that. But only birds survived. All these other experiments kind of led nowhere in the end. So what about color? This was then the next thing that became possible. Indeed, it's possible to determine the color of Archaeopteryx, which seems to have actually been mainly black. But we began the story with this paper, in fact, in Nature in 2010. And this was a combination, as you can see, of Chinese authors and British authors, mainly based in Bristol. And this is February 2010. This was the first announcement of how to determine the color of a dinosaur. And of course, it created a great deal of excitement at the time. There's Sinosauropteryx at the top left, which we were studying, reconstructed as all over ginger with a nice ginger and white stripy tail. That's what we're saying. And another team based at Yale University in the States, plus with Chinese collaborators, they were on the same objective. And they were working with a different beast called Confucius Ornis, and there's their reconstruction with a great diversity of colors and patterns, blacks and white stripes and a nice gingery crest. And so these two papers came out around the same time. It's unusual in the world of paleontology that we would be sort of chasing and competing in this kind of a way. By chance, we were a few weeks earlier. We came first, as it happens, although in the long run, it doesn't matter, but it's kind of nuts. Anyway, and the important point, though, is we are saying that that color, the reconstruction of colors and patterns in the image at the top is actually wrong, whereas the image at the bottom is actually correct, and we have the evidence to show that. And it's all about these structures which are called melanosomes. So in the title of the paper, Fossilized Melanosomes and the Color of Dinosaurs and Birds. So melanosomes are the key to the whole story. And most people are aware that one of the commonest pigments in nature is melanin. Maybe you're not aware, though, that there are multiple forms of melanin. So the black ink of a squid is a particular kind of melanin called sepiomelanin, whereas the dark color of melanin that we have in our skin and hair is called eumelanin, EU melanin. But animals with an orange or ginger color in their hair or feathers, that's a different kind of melanin called pheomelanin. So the different forms generate different colors. They may occur in different groups of animals, but interestingly, these two, eumelanin and pheomelanin, are widespread in birds and in mammals. And indeed, they occur widely in all other groups as well. The color of the scales of a snake or of a turtle are generally due to melanin. So we took an example here of a zebrafinch because it's got all the different varieties of melanin-based colors. And the ginger patch on the cheek, when you take a feather and look at it under the scanning electron microscope, and that's a 1 micron scale bar, so that's a millionth of a meter, it's about the limit of a normal scanning electron microscope. You turn up the magnification about as high as you can go. And in the areas of pheomelanin, the melanosomes are spherical, whereas in all the other areas of black, gray, and brown, and those colors come from eumelanin, the melanosomes are sausage-shaped. And a melanosome then is a structure, a hollow, or a capsule within the keratin of the feather. So feathers and hair are made of the protein keratin, as are your fingernails. So keratin is naturally clear in color, and it can only bear color if it has got melanosomes containing melanin inside. And the melanin doesn't just sort of flow around inside the hair or the feather. In your skin, your freckles and your dark skin color, the melanin is just dispersed within the layers of the skin. And of course, it can respond to sunlight and different parts of the world. People have different amounts of melanin. But in hair and feathers, it's always encapsulated, and the shape of the capsule is fixed. And that allows us to determine the fossils, because of course you can see it in the fossils. So we have data, we have evidence. So this is what we can call a chain of inference. That's a standard term in the philosophy of science. Here is the chain of inference. We have our fossil. You take a small sample, just like a millimeter or so with a scalpel. You put it on a stub, put it into the electron microscope, and you have a look. And this is what we saw in the case of Cirencester. They are all spherical, both solid spherical and moldic, meaning molds of where the spheres were. Because what we're looking at here, of course, are where the two slabs have been split open. And as they are split open, the feathers tear. And of course, the melanosomes in many cases will fall out because they are just loose little ball-like things. The decayed remnants of that melanin are there. But mostly we're seeing the moldic impressions because, of course, keratin, your fingernails or a feather, is flexible, is kind of solid. And to insert color into that, you've got to make a little hole and put so these are the little holes in which the color was. And you'll recall, of course, the spherical melanosomes at the top indicate ginger, and that's the reconstruction. So it's a chain of inference. And if you had thought when you came in this evening, science is about repeatable experiments, and therefore you cannot do a repeatable experiment concerning a dinosaur, that's not true. Science only needs to be testable or refutable. The nature of the claim has to rest on evidence, but you have to provide evidence that can be rejected. I can't prove this, but you can reject what I've done. And so the way you would reject what we have done is you would find your own specimen of Sinosauropteryx, take a sample, look at it under a scanning electron microscope of your own choice to make sure this isn't an artifact or something we constructed. And you would then also look at the modern evidence. You could say, aha, this is all very well, but this is only in zebra finches. Why would we apply that unique feature of zebra finches to all dinosaurs? Well, this relationship of color and melanosome shape applies to all birds that people have so far looked at, so thousands of modern examples. But we could be refuted if tomorrow somebody finds that this isn't true for certain bird feathers. And it's not just birds, because that's not enough. That would be like saying T-Rex sang with a beautiful song, because most birds sing with a beautiful song. That lacks logic, because of course you can't project everything simply down to the ancestors. But the fact is mammals show the same relationship as well between color and melanosome shape. So in fact, this appears to be ubiquitous to all vertebrates, as far as we can tell. If it occurs in all modern vertebrates, you can reasonably assume it occurs in all ancient vertebrates. So we have evidence, and therefore we can say that this reconstruction is based on much better than guesswork, which would have been true up to that point. It stood for 12 years. Nobody has refuted it. That's not very long. There's plenty of time for people to come along and pick holes in either of those steps in the chain. Either our fossil is weird, and this is not a generally replicatable feature in other fossils, or our scanning electron microscope is duff, and we're looking at some kind of photographic artifact. It has been known in many, many branches of science that people describe microscopic phenomena with great confidence, and then somebody says, no, it's just a bit of fluff, or you just sneezed on the slide before you looked at it. So that could be refuted. And of course, based upon the observation, the last link from the top to the bottom is based on that observation of the color at linkage and so on in modern birds. Okay, let's move on. This is the reconstruction then. So Bob Nichols is the artist who was employed by Thames and Hudson for my book. And he did these amazing artworks. And our claim then is that this reconstruction is the first time you have seen a really detailed reconstruction of a dinosaur, where we would argue everything you see is based on facts. And previous images of dinosaurs that you've ever seen have a fair amount of informed guesswork, let's put it that way. And so this was the purpose of the book, Dinosaurs, New Visions of a Lost World, published last year. Thames and Hudson, I like publishing books with them. They do lovely, lovely artwork, beautiful paper, beautiful print. And we decided then we would feature 15 beasts, and we'd take you through the story of each of those. And I'll just tell a couple more stories just to give you a flavor of what we know and how we do it. So the second beast then is Cytakosaurus, a very different kind of dinosaur. This is a plant-eating dinosaur. This is a parent with some babies, and the adult is maybe up to 2 meters in length, so it's still not very large. And just feast your eyes on all the detail here. The animal is not richly covered in feathers, as the previous one was, and yet there's a great deal of, well, at first not a lot of color, but actually a lot of detail of the color, the dark and pale areas, the spots on the shoulder, and indeed on the tail is this very weird collection of vertical reed-like structures. And indeed, we're making a claim these are feathers. They are there, they're feathers. And exactly how the animal deployed them is, of course, completely mysterious. And what about the babies? You know, there they are, confidently shown. We've got thousands of babies. These all come from China. Again, they're from similar age deposits to Sinosauropteryx, about 125 million years ago. And there are many examples like this one at the top right, showing multiple baby examples of the same species of dinosaur, Cytakosaurus. And the name means something like parrot reptile, because it's got this sort of beak-like structure at the front of its head. And so there they are. And this was one that a PhD student of mine studied, and he was able to he took thin sections of the bones, he was able to age them because they show kind of growth lines in the bones. And he discovered they were all 2 years old, except the one in pink, which was 3. So that was a big brother or big sister consorting with younger siblings. What's going on here? There are so many of these aggregations. In all cases, they nearly always are pointing in the same direction. They're in a tight cluster. And so the general interpretation, and the key point you need to know is that the gray colored rock around them is pure volcanic ash. So this is not like those lake beds where the volcanic ash has been reworked by water movement. This is airfall volcanic ash. And indeed, the Chinese call this locality, Lujiatun, the Chinese Pompeii. And their interpretation, which sounds highly plausible, is that all these little critters were caught by falling volcanic ash. But 1 or 2 of them, thank goodness, are preserved in the lake deposits, because falling volcanic ash, just as at Pompeii, doesn't preserve very much. You'll know that if you've been to Pompeii or read about it, you've got the skeleton, you've got the body shape kind of preserved because the ash molded the body, but the soft tissues have pretty much all gone. And so here, except in the lake. So here is an example of an adult, 2 meters long. This one happens to be in the Senkenberg Collection in Frankfurt, and it shows all the detail that was used to make that full-scale reconstruction, including the skin over the body. There's some gut contents in there, and the skin over the shoulders and around the neck and behind the legs shows it's paler, but with blotches of color. This animal shows counter shading, meaning the belly is pale and the back is darker in color. And that's a very standard feature of many animals, which is meant to play tricks with the light. So to a predator, it makes the animal sort of partly blend with the background. And particularly the low level of the line of division between pale and dark suggests that this was a woodland living dinosaur, because this is what we see in modern mammals that live in woodlands, whereas mammals that live on the open plain, the line between pale and dark is kind of halfway up the flank. And that means when you're out in the sunlight in particular, you're pale underneath because there will be a natural shadow cast by your body, and you're darker on top because the sunlight is burning down on your back, which kind of flattens your profile. So the predator, if you don't move much, the predator, is there anything there? Can't quite see. And it's supposed to have the same effect. And so here are the 4 body views of the adult by Bob Nichols, showing the distribution of color, counter shading, and these weird feather-like things on the back. And all that detail of the speckling, the mottling, and such like is there in the fossil and reproduced here. So there's the full reconstruction. We have the babies, we have the adult, we have the range of color of the skin. I should have said those brown colors and dark colors, they're all made with melanosomes in the skin tissue, in the fossil. So there's another dinosaur where we know a bit of detail. This is not a dinosaur, this is a pterosaur. So I'm going to give you another example. In this case, this is a flying reptile, and we worked on this. So this is another project between Bristol and a different team of Chinese researchers. And we were working on this very jolly little thing. It's about the size of a tern, small seagull, that sort of size. And it's all covered in whiskery, feathery things, and a variety of brown colors, all of which we know. And here is our paper in Nature, Ecology and Evolution in 2019. And we're making a claim about these structures in pterosaurs. We're saying these are feathers too. Some people say you're going mad, you're seeing feathers everywhere. You'll soon be describing fossil fish with feathers. And, don't be ridiculous. But we're making a definite point. Actually, we believe these truly are. And it's not unexpected because the pterosaurs are not dinosaurs, but in evolutionary terms, they're the cousins of dinosaurs. So they're very close relatives. And what surprised us was when we began looking at the structures in detail, we expected just to find simple whiskers like E. But then we found some with tufts at the top or tufts halfway or branching from the bottom, like a regular down feather. And so, in fact, all these four structures we could identify in birds and in dinosaurs. And so basically in the paper, we're saying we can't distinguish these from feathers. They have all the chemical structure of keratin, they contain melanosomes, they have everything we would expect. And therefore, because they're in close relatives of dinosaurs, which branch away from each other at a particular point, why could it not be that their common ancestor had feathers? And we have feathers all the way from that early ancestral point right up through into birds. And not only that, we can tell the color. And so here is Bob Nichols' reconstruction of that pterosaur. And this is an insect eater, and you can see he's looking unusually happy to have spotted a lacewing, which he's about to gobble up. And that the range of shades and colors and the distribution of these little whiskery feather-like structures, again, are all based on fantastic fossils from China. So just in case you thought everything was from China, here's one from Brazil. This is one of the later pterosaurs, which became completely huge and ridiculous. Later in their evolution, the earlier ones were a more sensible sort of size. This thing has got a wingspan of about 3 to 5 meters. So, not far off the width of this room, probably, or at least half the room. And more impressive and weird is the skull, the head. And so there's a fossil in the middle, and there's a model of the fossil skeleton in a museum in Brazil. And it's got this extraordinary large but lightweight structure. It's all really hollow. And these struts supporting something in the fossil. Let's look a bit closer. It's actually a skin sail. So it's got this extraordinary sail made of skin. And when researchers looked at it more closely, they found it was densely covered in short feathers, which contain melanosomes. Hence a variety of reconstructions showing different patterns in different species of blobs, circles, and different shades. And indeed, the alignment of the melanosomes suggests that they were forming some sort of surfaces. So they were almost forming kind of nano surfaces. And so the suggestion was that they were perhaps even photoluminescent, that they were perhaps capable of absorbing energy from the sunlight in daytime and then transmitting it in the early evening, just like glowworms do. And so here's the reconstruction of two pandactylus, absolutely huge, 4 or 5 meter wingspan, and this extraordinary head, which is massively lightweight, but nonetheless it is very huge. And the only assumption we can make is that all these patterns and colors are maybe partly camouflage, but partly, we're certain, particularly if they could flash on and off, there's something about mating, something about sexual selection. The final example is from Canada, from Alberta, and the Athabasca tar sands, which make a huge amount of money for the Alberta economy. And they are mined in huge quantities and essentially squeezed to get the oil out. And this is not like North Sea oil. You just go in there and dig up this filthy stuff and squeeze it and boil it, and you have enormous amounts of oil. But dinosaurs lived there. And a huge skeleton was found a number of years ago, and my former student, Don Henderson, who's got probably the most dreamed of job for every 7-year-old in the world, which is he is head of dinosaurs at the Royal Tyrrell Museum in Alberta, which is one of the greatest dinosaur museums in the world. It's located in the middle of Dinosaur Park, and it's called Dinosaur Provincial Park because it is just full of dinosaurs everywhere you go. Here is the skeleton of this thing, and it's a very large armored dinosaur, and a great deal of detail is preserved with it because the deposits were rich in oil. This again seems to have helped exceptional preservation of the keratin layers that cover the bony osteoderms of the protective skeleton. So this is a kind of skin armor, just like crocodiles have got. They've got plates of bone that develop within the skin, but the bone is not exposed on the outside. It's covered with keratin, just like the horn of a cow. And keratin can carry color. And when they found this, they were quite surprised that in some parts, like at the back there, it looked a little bit pinkish or gingery. And indeed, when they looked more closely, they mapped out these osteoderms as a very regular pattern, different types, sort of round ones over the back and some kind of pointy, pretty scary looking ones around the neck. But they also identified pheomelanin in the keratin of the plates. And so here is the reconstruction, a very gingery looking tank of an animal. And it's got these extraordinary spines, and particularly from the front end, would be quite a hard animal to prey upon. It's a herbivore, but would be food for Tyrannosaurus-like carnivores. And to give you an idea of size, those blades over the shoulders are about 1 meter long. So this is Boudica, or the Roman soldier's worst nightmare. Something like I don't know if there's any truth in the chariots of Boudica with these great scimitars on the wheels. Probably not. But here's a dinosaur that had already thought about it long before. And the gingery color, extraordinary. You know, again, we have all of that detail. So I just want to wrap up with a few words on my third theme, which was the scientific evidence. I've talked about the opening up of China, how that has really transformed the subject with access to these amazing fossils. I've talked about the specifics of color, and that's a key feature of the new book, and really going into depth and talking to all the people in different parts of the world doing the work and trying to document a big move in the nature of our science. But the third point was, how do we know about the life of the past if we don't have a time machine? Well, I've already given you the evidence for color, and it's really important to be clear about this idea of the chain of inference, because in most of science, indeed, you can go and repeat your observations and retest. And that's the normal way to do it. But I've argued here you can do just the same thing with the fossils. And another case I was talking about, of course, was flight. How on earth can you tell whether these early feathered dinosaurs could fly or not? Well, I believe you can, because we know the rules of flight, the nature of aerodynamics, the biomechanics of how things fly. It's the same as how airplanes fly. There's a very definite set of rules. And simply having the correct size of wing relative to the body mass is a very good starting point. And both of those, I believe, you can determine pretty well in the fossils. We can also determine speeds and bite forces, feeding styles, growth rates. So in fact, all of these things now we can pretty much pin down. And in some cases, we have double lines of evidence. So I'll just talk you through this super fast. Speed, you can do it from trackways, because the faster you run, the further apart your footprints. And as long as you know the size of the running animal, you simply measure the distance between the footprints, the stride length, and that calibrates very precisely to the speed. So when that was done for T-Rex, 27 kilometers per hour. A second approach was to consider the dimensions of the limb bones. So if you think about modern human beings, and although we're looking at the Winter Olympics right now, but think about the Summer Olympics, the sprinters have enormous tree trunk-like muscles in their legs. And it's the diameter of those muscles that give them the power. And there is some sort of relationship between the diameter of those muscles that power the running and the speeds that they can achieve. I've got very weedy leg muscles, so my running speed is very slow. And so this diagram is by John Hutchinson at the Royal Veterinary College, plotting a measurement between body mass and the mass of those limb muscles, or should I say the mass of the limb muscles and the speed that can be achieved. And the image here is meant to represent the 6-ton chicken. So a chicken normally weighs half a kilogram. And we know the kind of speeds that chickens can achieve. They are quite fast if you've ever tried to catch one. And this is a good remark to make in an agricultural comment, because most people think of a chicken in Sainsbury's and that doesn't go very fast. A real chicken runs fast. And Hutchinson's thought experiment was, if we scale it up to 6 tons, the weight of a T-Rex, could it still run with that similar kind of velocity or relative to its body size? The answer is absolutely not. It absolutely could not, because the volume of leg muscles needed by a 6-ton chicken would be beyond the bounds of possibility. They would have to be so huge, they would exceed its body mass. Not possible. T-Rex could only walk along. And although 27 kilometers per hour may sound fast for a giant animal like that, that is a relatively slow walk, as it happens. But notice it corroborates an independent estimate. One other example, both methods shown in the one slide, bite force. We know of many examples where T-Rex has bitten into the bone of a herbivore dinosaur. And here's one example of a piece of bone with an American cent, which is about a centimeter or so across. And that gouge is a fresh looking impression made by the tooth of a T-Rex. And we know that because people have poured molding material into that gouge, let it set and pulled it out, and you have a perfect tip of a T-Rex tooth. It goes in about 3 centimeters, so you can do physical experiments to drive a model tooth into a piece of real bone. Doesn't matter what the tooth is made of, but you must drive it into a piece of cow bone or something that mimics the dinosaur bone. And the kinds of forces are something like 12 to 15,000 newtons. Secondly, you can do computing models. So here's a 3D model of a T-Rex skull. And Bates and Falkingham did the physical experiments using software that we commonly use in medical applications for estimating forces and strengths of limb replacements, knee replacements, hip replacements, that kind of thing. They used the same methods to model bite forces, and they came up with that amazing range of 35 to 57,000 newtons. So this is equivalent, if I remember rightly, to something like 5 tons of mass. And those bite forces are way, way beyond anything that any living creature is capable of. And with those digital models, you can test the skull to destruction because you know the material properties. Now I have one more slide on that. My colleague here, Professor Emily Rayfield at Bristol, does just this. And her argument would be, if anybody doubts those calculations, she would say, okay, do you go in an airplane ever? Or have you ever been in a multi-story building or been across a bridge that was built after 1950? Because if you've ever done any of those things, you've trusted your life to the validity of engineering methods like finite element analysis. And all the testing, the stress testing of modern structures is all done by engineers and has been for the last 50 or 70 years using these methods. She uses these methods on dinosaur skulls. Therefore, we know how they work. They work on material properties. You can make your airplane of aluminium or steel or plastic, or, you know, and it's used, of course, again for limb replacements. If somebody says, could we make this hip replacement all from plastic? You'll test it and find, no, that probably won't quite work. We need to modify and do other things. And so the method works. And so using that, and there's some of her diagrams, you can do those kinds of studies. So I've tried to weave together three ideas. We've got fantastic new sources of fossils, which lead to all sorts of wonderful experiences and collaborations and developments with colleagues around the world. This is very exciting for young people coming into the field. It's not just, though, the discovery of new fossils, it's actually a discovery of a whole new way of working, a scientific way of working, which is difficult to grasp when you're dealing with things that died out 66 million years ago. But we would argue using the laws of nature, which are constant. Physics doesn't change. Gravity, generally, people accept, doesn't much change. And the nature of aerodynamics, the ratio between wing area and body mass, why would that be different in the Jurassic than today? So it's reasonable to assume that they were the same. And so actually, I've tried to show you examples where we can determine quite a lot about the life of the past. And what use is it? It's just fantastically good fun. That's it. And I wouldn't go any further than that. But it's a field that attracts a lot of people into science, and I take this into schools and give similar talks. And it's a sort of detective work as well that gets young people really excited. So I'd like to thank you for your attention, and thank you also for your patience at the start.
Are there any questions on the floor? Yes.
I'm not quite sure. Why did feathers start to evolve in the first place?
Yes.
Because obviously, originally they had no benefit in flying. So, do we think it's because the weather was colder or something?
Well, you've hit on it. You're right. It's insulation. Flight is a very distant second or third. I would say a third, because the three main functions of feathers are mainly insulation. Secondly, display, because they can carry color. Think of the tail of the peacock. And that has big evolutionary advantages, of course, and for camouflage and other purposes of color, and finally for flight. And so I think in both cases, the origin of hair in our ancestors and the origin of these simple feathers, simple whiskery feathers in pterosaurs and dinosaurs, happened at the same time, about 250 million years ago. And I think that was a key point. There'd been a huge mass extinction event at the end of the Permian. Life was beginning to recover and rebuild, and already warm-bloodedness had emerged in a number of different groups independently. And that was somewhat advantageous, and to have some insulation was helpful. And so then I think it spread dramatically because the world had been cleared out by the mass extinction. And we had the origins of endothermal warm-bloodedness in the ancestors of mammals and the ancestors of birds, and they were in a kind of ecological arms race, hunting each other in the same ecosystems. And so it seems that everything was sort of speeding up around the same time. Thank you very much.
Richard?
You've shown us animals that are black and white and brown and things. I was wondering whether there were greens and blues and yellows. And
We don't know. And the reason we can't yet say is that those colors in modern birds come from food-based pigments, such as carotenes, which give yellows and reds. And think of the flamingo, if they are starved of their regular diet, which includes shrimps that carry red coloration from algae, I think, they're not pink. That color comes direct. And the greens and purples come from porphyrins, which are another food-based color. But the only thing I can say is that where you have melanin-based colors, they dominate. And you only get the greens and yellows and other colors in what would be a white patch. So in this sort of reconstruction, you don't get competing colors, I don't think, in birds. So if you've got a black or a brown, you know, if you think of a mallard, it's got all the different colors that you mentioned. But the flashes of green and purple, they would be restricted to otherwise white patches of feathers. But we can't yet detect those because they somehow do color the feathers without being in melanosomes of any kind. So, but and chemically it's difficult because organic chemicals break down very fast. Yes.
Just a simple question. Is it reasonable inference to say that any creature that has a wide variety of color necessarily will have color vision too?
That's an interesting question. It depends who the color is aimed at. So of course I could give a ridiculous answer, which would be to say flowers have got glorious colors, but they don't have eyes.
Yeah.
They're aiming their color at bees or whatever. I think though you're right that mostly colorful birds and mammals would be aiming at other members of the species, but we would also have to ask the question, could some of those colors or patterns be warnings, for example? So I think maybe in the case of some snakes, I don't know if they all have color vision, but certainly their bright colors are more, I think, for warning other organisms, not predators exactly, but warning mammals and things in the habitat, don't step on me. I'll bite. And so I think most other animals are very attuned to seeing those stripy red and white snakes, and they keep clear of them. But whether the snakes themselves could see the colors, I don't know. If you're postulating sexual selection, then definitely, because all the lovely colors and flashes and special effects that birds can do, I'm sure the female birds, they can look at them in a cynical way. So, as David Attenborough was saying, I've seen it all before. They can at least see it, I'm sure.
At the back.
Do you think that global warming and the melting of permafrost and ice caps is going to reveal a lot more of the history of this?
Very interesting. Yes, I think certainly for people who work on mammoths, and of course recently we've been reading a lot about that. My kinds of beasts are much older, so they're not preserved in that way. I'm not sure how old the permafrost goes to, but probably no more than maybe 500,000 years, something like that. So this is much more Neanderthal people and mammoths and woolly rhinos and that kind of thing. But I think you're right. Certainly, if you've read anything or seen anything about how the Russians collect their mammoths, they often chance upon the most amazing things in the banks of rivers. And this is where the permafrost has melted, and the earth has just fallen away. And there's a whole carcass of a almost perfectly preserved mammoth in some cases, with the flesh and hair and skin and so on.
Barbara.
We think of melanin as protection from UV. So does this, the fact they have so much melanin, does this tell us something about the climate of melanin or the strength of UV?
I'm not sure. I don't think generally melanin colors in hair or feathers are so much related to protection in that sense. I did read somewhere that a lot of, so in birds, for example, the parts of the feather that contain melanin are tougher than the parts that do not. And so seabirds, which are generally white in color because they're in that environment of sunlight and reflections from the seawater, often the tips of the wing feathers are black. And that's so if they hit a cliff or something, so they say, it provides physical protection. But I don't think those colorations at the end of feathers, for example, would relate to temperature control within the body of the organism particularly. But I think the color of fur, the color of hair, yeah, that does have some effect, doesn't it? Comparing the different species of bear. But then maybe it's even more about the kind of detailed structure within their layers of hair and trapping air and stuff like that. And whether you're black or white, reflecting the sun, absorbing the sun. But I think in most of these cases of feathered creatures, probably there's much more to do with camouflage, sexual selection.
Are there any questions on Zoom?
No.
Yes.
In your first part of it, why was there such sort of cultural resistance to the idea that these Chinese discoverers could be the missing link? I mean, given that
Yes.
we know they got their entry.
Yes, yes, yes. I know, I'm bewildered because it seemed patently clear, obvious at the time. And Huxley had said it all 100 years before. And generally he was quite a wise person. And but people had chivied and twittered, and they had all sorts of weird ideas about the origin of birds. They'd been all over the place in the intervening century. And even in 1990, there were still many people who would say, oh no, birds are something special in evolution. They must have taken hundreds of millions of years to evolve, and you can't have them just springing forth from dinosaurs. But No, it just seemed incredible. And there are still some holdouts. Even today, there are still some people who say, well, it looks like a feather, but it isn't a feather. And I don't know what more you can say in those cases, where you just have to say, oh, think what you like. It's, yeah.
Any more questions? Yes.
Feathers have a sort of Velcro construction, don't they?
Yes.
Where did that come in?
I think it's as soon as feathers were used in flight. So some of the contour type feathers that the earlier dinosaurs had, the ones that couldn't fly, they were often quite simple barbs. So you've got the vein in the middle and then the lateral barbs. And there are many bird feathers today where the barbs don't interlock, but those would just be nothing to do with the wings. But once a feather is entrained as part of the wing, it's got an enormous force acting on it, because as the wing is flapping, the main power move of the wing is the down back. That's what makes the bird stay up and go forward. And as the bird is pushing its wing back, the air is forcing under the feathers and will break through if it possibly can. And so those forces and holding the feathers, and there's a sort of roofing arrangement on a bird's wing, of course, the primaries that stick out furthest are then overlapped and held in place by an overlapping set of feathers, and there's more feathers, and so multiple layers, like layers of thatch on the roof of a cottage, and to just really hold them firm. And so all of that arrangement of interlocking is so essential to hold, because if the wings shredded as the bird was flying, it would fall out of the sky. So they have to preserve that continuous and complete membrane. It's almost like a membrane. It's not really, of course. And hence, of course, when they're walking around and if they fall out of a tree and the feathers get caught up, they're preening and all that, moving their beak down to get the feather locked back into its correct shape, because otherwise they couldn't fly.
Any more questions? I noticed in the graphs you showed us the development of from Sinosauropteryx up to the thing that actually took off.
Yes.
What sort of period of time? I noticed along the x-axis and no actual time frame.
So I think those evolutionary things is about 50 million years.
50 million years.
So the origin of feathers and early stages and the acquisition of all these bird features, all the special features of birds. I didn't say this, but when I used to teach this, we'd say, here's Archaeopteryx, and let's look at this thing in detail. And we could make a list of about 30 specifically avian features, bird-like features. So obviously feathers, but hollow bones and the fused clavicle, the wishbone. And there's a whole string of other features, the way they fold the wings back, and they can fold the wrist in a way that we can't. All sorts of things. But subsequently, thanks to these Chinese fossils, all those 30 uniquely avian characters are all found up to 50 to 60 million years earlier in one or other of these pre-bird dinosaurs. So it's been the most extraordinary, and yet that's not unexpected, because of course that takes away that miracle thing that people used to put on Archaeopteryx. You know, here it is hatching out as a total bird. And so for creationists, they loved it because they could say it was created. It can only function as a bird if it has got all of these 30 features operating together. Now we know that in fact, each of these 30 originated at a different time, often for maybe different reasons, in fact, and then they become connected and incorporated into this extraordinary, efficient flying machine. But it bears out what Darwin would have said. He would have said, no, they're not miraculously evolving with this extraordinary set of innovative features that have just suddenly sprung up, you know, like a bird hatching from a crocodile's egg. In fact, we can track it through, and that's it. Yes, 50, 60.
Thank you very much. Thank you. Well, thank you very much for an absolutely fascinating talk on a subject we know very little about. And thank you for coming this evening. So, safe journey home. Thank you very much. Please don't forget, the book is available in Waterstones, Dinosaurs, New Visions for a Lost World.